Okay, so hello everyone. My name is Francisco Borja de Saavedra, and I have an industrial PhD at Aerospace in collaboration with the university. And I'm here to tell you about the sizing, direct characterization, and simulation of externally wetted ionic liquid electrospray thrusters. So initially, I'm going to start with the problem motivation of this project that we have at the company. And it's basically that, well, first of all, we know that onboard propulsion, especially in LEO, is quite an enabler, right? Like with propulsion, you can do like maneuvers that are critical for the mission, or you can like go for other mission objectives. You can contribute to a sustainable space environment by collision avoidance and decommissioning. So I think it's pretty well known that propulsion is quite an asset for constellations and also for single satellites. So the motivation here is that despite we have seen in the last years like an exponential growth of like small satellites, especially like nanosats, CubeSats, and so on, as you can see in the graph, like it's the lowest curve, like really not so many are actually carrying propulsion on board. So basically only a few % of them are actually have a propulsion system. Basically, as you can see here, like picosatellites, nanosatellites, and well, mostly picosatellites and nanosatellites have an adoption rate of propulsion of, well, it's less than 6% or about less than 10% for sure. Whereas as you go for like larger satellites in the order of tens of kilograms, or even larger, like 75 or more than 90%, or absolutely all of them mostly, have propulsion. So if you don't have propulsion, the thing is you don't really have any maneuverability. So that lowers, of course, the functionality of your platform. You can get like lesser revenues or even like more mission costs, because if you reduce the lifetime, you might need like more satellites to accomplish a given objective, right? So basically, we are seeing this gap, right? Like this is the motivation. Like, why do small satellites not carry propulsion? So what we have identified is that, first of all, these platforms like CubeSats are the most well-known, and picosats and so on, are like really variable. Like they have like very different sizes, power, like volume, and they are like typically quite constrained for conventional electric propulsion systems. So, and we have also seen that there's quite a lack, let's say, of dedicated knowledge in that like propulsion and orbital dynamics are inherently coupled, so you cannot like really study them separately. And basically, many times you can go to the market and get like a propulsion system, but you see what you do with it. Basically, you get the propulsion system, then you can see what you can do with it. So basically, from Aerospace, like our solution is to do kind of both things in the hardware and the software department, let's say. So first of all, we are developing Athena, that stands for Adaptable Thruster for Electrospray, based on Electrospray for nanosatellites. And it's meant to be a custom propulsion system that is, so it's a scalable propulsion system that is customized for every mission. And it's gonna, since it's based on Electrospray, it's quite promising, and it could have like the highest efficiency in the power class, and also go to like very low powers. And we're also like developing other like software services like Go and 360. I'm not really going to go into them that much, but it's basically about concurrent engineering. So what we do is try to iterate like in the design and fabrication of the thrusters and their operational point for each mission. So like customized for each mission, also with software. So what we do is kind of like solving the inverse problem. So instead of taking a propulsion system and see what you can do with a given platform and make many studies, what we do is kind of the opposite. Like, we want to know first what is your mission, what is your platform, what are your constraints, and then make a custom, like optimized propulsion system for that. So within this project, let's say, the objectives and well, the methodology of my thesis in particular, that is within this whole project, is, well, first of all, to develop like a concurrent preliminary design tool for a scalable electric propulsion system. As I said, we want to have a system that can be scaled to any size. So the first thing to know is like how we can do this. Like, what are the propulsive requirements for the mission? How can we cover all of it? So this is like one of the first objectives. Then it's not so related to astrodynamics, but the next objective of my thesis is like the development of direct diagnostics for these like externally wetted ionic liquid electrospray thrusters, to be able to like characterize them, their performance like in full, so measuring thrust and propellant consumption. Then with all this, so basically with this concurrent approach of having, let's say, the preliminary requirements for the propulsion system and the performances of our first prototypes, the idea is that we can like size and characterize the next generation of thrusters. So it's of course an iterative process, and it's about keep improving the system to adapt, as I said, for any mission, but also with the hardware side of course having the performance actually characterized. And then last of all, this is a kind of a new objective that has happened, let's say, during the course of my thesis that was not initially planned. But it's about the simulation, direct characterization, and mitigation of electrospray emission effects on spacecraft charging. So basically, electrospray is a bit different. Of course, it's not a plasma propulsion system. You have basically an ionic liquid from which you can extract like positive and negative ions. So in principle, if you do it properly, you can emit alternatingly positive and negative ions, so you don't need like a cathode, you don't need a neutralizer. So if you do it properly, you could have neutralization of your plume without needing an external cathode. The thing is, the spacecraft charging effects are like quite fast. They can happen in the order of milliseconds or microseconds even. So you definitely want to take this into account, because even if you can alternate the current, if you do it like every half second, you might be charging your satellite because the plume is not instantaneously neutralized. So there's the other objective. So some intermediate results, as I'm in my second year of the PhD. So about the first objective of the concurrent preliminary design tool, this has been accomplished and is the Go software that I mentioned before in the beginning. It's basically, as I said, it's quite preliminary. So it has some simplified dynamics. It includes like secular propagation. And it's basically multiple constraint optimization of either the duration or the propellant for different maneuvers. And of course, we are using for now the propulsion model of our thruster of Athena with the latest results that we are characterizing, basically. And as I said, the idea is to solve the inverse problem. So in this tool, what you have as input is all the data from the platform, the constraints you want to put to the thruster. So you actually give the thruster envelope as an input, your initial orbit and what maneuvers you want to do, what constraints do they have, and so on. So basically, this is just like a propagator solver. Sorry about the fonts, because I think some things have moved around. So basically, it's like a propagator with a solver for the maneuvers with an optimization layer like all around it. And the output, as I say, is the idea is to solve the inverse problem. So actually, the output is the optimum thruster. So the propulsion system is actually the output. Of course, you optimize at the same time, like the design, let's say the preliminary design of the thruster, its operating point, but also the how to do the maneuvers. So it's kind of like everything is like optimized at the same time. So yeah, this is basically Go. So if in few words, it would be like a concurrent mission and propulsion system design tool. As I said, it's preliminary, and it's made to be like quite user-friendly, fast, and robust. So we made a web application for this. It has been benchmarked against GMAT. It's open access, so it's free, so everyone can like sign up and you can use it. And we're actually in the beta version, so it would be nice if you would like to, I invite you to actually like try it and give us feedback, because we really want to improve it a lot. So more results for now, like about the second objective. As I said, this is not really about astrodynamics, but it's about the direct diagnostics. So actually thrust and propellant consumption measurements of the thrusters. So the first thing that I did is basically thrust measurements, right? So the thing is, electrospray thrusters are really small, and the thrust that they produce is of the order of micronewton. So this is quite challenging for doing a thrust balance. Of course, you can do like torsional thrust balances, and you have other options. But we thought we could do with a commercial off-the-shelf, basically analytical balance that are used in lab, of course, for many other applications. What we did is actually take one of these and actually adapt it for vacuum operation. That's the first thing that we did, and we did some preliminary tests with the thruster, as you can see. So you can see in the left, like the balance as it was, as we bought it, and then on the right, like the balance, like basically dismantled and like adapted for vacuum. And you can see cables because the electronics had to be put outside and so on through the feed-through. So sorry, I didn't say, but the right side is inside a vacuum chamber. Actually, the vacuum chamber here at Uni, because as I said, this is a collaboration and we use the facilities here. But you can see that little thing on the plate of the balance is our thruster, is one of the very first prototypes. and it has cables and so on for like the supply, which is of course not ideal because you're measuring in a balance that of the order of micronewtons, so the tension of the cables is not really nice to be there, but it was just like the very preliminary test. So since we saw this thing of the cables, of course, like even the slightest, as I said, like even the slightest perturbation you're gonna see because it's micronewton. So we did this vacuum environment study to see if this balance was actually like fit for vacuum. And what you can see here is basically like a long pump down in a graph in time of a long pump down. And you can see in the y-axis like the rate of change of the force, because as you pump down, the buoyancy basically of everything in the balance goes down. So the force that you actually see in the balance goes down with the pressure. The idea is that it has to stabilize at some pressure so you can actually make the measurements like properly, right? And as you can see there, like, well, there are two spikes when you turn on the primary pump and the turbo pump. But then after 1 hour and a half or 2 hours, we get like variations, like so stabilization to much less than 1 micronewton per minute, which is more than enough to already test. So we started doing like more advanced experimental setups. As I said, because the main thing for the setups was to avoid the cables, so to try to reduce the perturbations as much as possible, because as I said, this is really, really small forces. So what the setup you see in the screen is basically, well, we added some adapter plates and other things, but basically that PCB that you see is basically doing the connection through with an MHB cable with some liquid connectors. Basically, you have like a cup of Galenstan that is a conductive liquid, and then you put on the liquid some kind of wire that is on the PCB, and then you can make the connection with the liquid without the tension of the cable. So this could be a solution for avoiding that. But you can see in the graph below that we saw some kind of decrease in force when we did this that we haven't really understood yet. Just by putting, even without a load, so even without the thrust or anything, just from the liquid connector, we would see this unknown force that we haven't really figured out yet. But it's just because of putting some voltage between them across the liquid connector. So this we had issues like this because, as I say, it's quite complex because the forces are really small. But then we said again, the problem was the tension of the cable, so we could either try with a PPU or something else, or we could also use like very, very thin cables. That was like the last setup that we did. And I don't know if you can see it there, because basically we did the connection with just a single strand of copper. So instead of having a whole cable with everything, we use a single strand of copper. And since the electrospray works at high voltage but very low current, it's not really a problem. And we actually, so with this setup, we were actually able to make the first thrust measurements of like really thrust measurements of an externally wetted electrospray thruster. And you can see it there, that we vary the voltage from like 1.2 to 1.7 kilovolts, and we can get forces from about 5 to about 23 micronewtons. You can see in the upper graph like the emitted current, again, against voltage. And as I said, it's really, really small. It's like some hundreds of microamps. So basically, of course, we checked before starting the test that we were actually like the balance was really stable with the thin cables, and that the thin cables didn't have an impact. So basically, based on this, we get thrust to power ratios that are actually relatively high for an electrospray, though. They are good in terms of thrust, but they aren't as good, let's say, for an electrospray thruster, since it's supposed to be high efficiency. So basically, if we had like a 50-50 distribution of monomers and dimers in the ionic liquid, that is quite ideal. Let's say in the pure ionic regime of the emission, we would be about 50% of thrust efficiency, which is pretty high. But of course, these are just one of the first prototypes that we have like characterized almost fully, and we are characterizing fully. So I mean, the emission is not going to be 50-50 for now. That's what we want to achieve. And as I said, this is if soon we might get something like this, so a thrust efficiency of like 50%, that is pretty high for a thruster that in this case is about well, less than 1 watt. So the idea, as I said, is that we can cover down to picosats and so on. So basically, these are the main results that we got until now. And the next steps, well, for the first objective, that is the preliminary design tool, we want to make a lot of improvements regarding the web app, of course, but also the back end of it, that is actually what's really in my PhD. And we want to generalize also for other propulsion systems, because right now, of course, it just has our propulsion systems, but we want this to be like a tool that anyone can use in the space community, and with which you can optimize all thrusters that have some variability, some control parameter, basically, that you could optimize preliminarily with this, concurrently with the maneuvers that you want in your mission. So about the direct diagnostics, we have seen, since the balance I'm using again is an analytical balance, it's a vertical balance. If you fire long enough, you can also measure propellant consumption, because you can see the decrease in the weight of your whole system. So that's the next thing to do regarding that. It's basically ready. We just didn't have the time yet. So with propellant consumption and thrust, of course, you could have the whole performance characterization of the thruster. And as I said, with the preliminary design tool and the results from these first prototypes, like the full performance, we would do like the sizing and let's say the next generation thrusters that we are designing now. This will help design them, and size them, and then we will do the performance characterization with this system. Again, like later, not yet. And also about the last thing that might seem a bit like unrelated to the other things, but is fundamental to, as I said, to the design and the development of an electrospray propulsion system, is this simulation and characterization and mitigation of spacecraft charging. We actually have started this already, like with some preliminary simulations, and we have built like a charge sensor, so we can have like direct. We can in a way make a setup that contains the thruster and like bias it on purpose as if it was a spacecraft that is biased up there, like with spacecraft charging, and we can actually measure it in terms of the emission. So I don't have like results to show yet, but it's also being started. And that's it. I don't think